Good evening, everybody, and welcome to a long lost Sky Tour live stream. We need to be here. We need to do this. I'm glad you all are with me. And of course, we always have Daryl with us. Daryl Mason, how are you?
Hello, Mark. I'm good, thanks. You? Hello, everybody.
Doing just fine, thank you. Just fine. Um, so it's been a while since we've streamed, but it's also been the monsoon out there, so no harm, no foul. It's not very good. Um, so that's it. That's why we haven't streamed. We also we changed the camera. The camera is now a camera that has smaller pixels, so that means that we get more detail per square inch, so to speak, by almost double. So we have a higher resolution camera, and we also have a field of view that's a little bit more magnified. Okay, so it's a little deeper field of view and smaller pixels. So we've got a double whammy that's going to help us. So when we do longer exposures and stacks, we're going to see amazing detail in some of the things we're looking at, and I'm really happy about that. I want to say hi to a whole bunch of people that are already here. Renee Cruz was the first one. Good job. Good to see you. Cosmic Ray's with us. Hey, Ray, how are you? Tim F is here. Marco's with us. Native NC, how you doing? Good evening. Haven't seen you for a while. Good to have you back with us. And we have Cyclone is with us. Nice to see you, man. And Alicia Vieras is here. And you know who's with her is Darlene. Hi, Darlene.
Hi, Darlene.
Darlene is the coolest little kid, man, and she is, we're probably talking to a future scientist. Darlene, you could change the world, so don't lose sight of that. You could change the world, all right? So before you fall asleep tonight, and I know it's late for you, just think about that. You might be the one to change the world. I have a lot of faith in you, and you've got a good book to start you off. Anyway, so it's nice to see you guys. PG is with us. That is Petita down in Pennsylvania. Robin Curtis is here. Hi, Robin. I'll take a look at the logo that you mentioned. I'm not sure where I'm supposed to look. She said to me, go... oh, yeah, the SkyTourShop banner. Okay, thank you. I saw that what you're saying. Yeah. Yes, our SkyTourShop up here, you can see it. This up here, that right there. We have an Etsy shop on SkyTour now that you're all welcome to go and enjoy. And if you want, you can purchase some stuff up there if you like. I think it's really cool. And there's a lot of things up there that you can get that I have a feeling you'll enjoy. We have over 100 products online now. And we're making up more all the time, so just about 100, and it's all things relating to photos we've taken. So it's all our original work for you to enjoy, if you wish. I know that several people bought these giant blankets we have with the Christmas tree nebula on it. What a Christmas gift that would be, huh? Can you imagine that? Get a Christmas gift of the Christmas tree nebula on an 80-inch by 60-inch fleece blanket. It's the coolest thing, and it's warm. I know that sounds like a sales pitch, so I guess kind of, sort of, but I'm just telling you that because we make these. We actually take our photos and apply them to this whole product line of things. It's so cool. Susan Woodcarver is with us. Hello, Susan. So nice to see you. Susan's one of our patrons as well. We have a patron list, by the way, that we would like to see it grow. We've got a lot of people that are definitely worth paying attention to. Here they are. We've got John P., Izabela M., Ali B., Chief McCyber, Vera C., Ronald T., Martin W., Raymond B., Cindy M., Susan W. Guess who that is? That's you, Susan. Shh. And we have Diane H. Okay. We'd like to grow that Patreon list. We'd like to get it up maybe, to like maybe 10 times that size. Not sure how to do that because I am the astronomer. I'm not business guy, so I don't know how that works. We need a social media guru is what we need. And if anybody out there knows a social media guru, someone who can work with us, and I'll tell you right now, we're willing to pay someone to help us get our word out because we have big plans. We want to create a mobile observatory that we can take around the country, bring to college campuses, bring to elementary schools, bring to other places, parks, anywhere in the country where we can set up impromptu star parties with our telescope and show them the universe live right there. So even under light polluted skies, we'll be able to show them the most amazing things because we can cut through that light pollution to a good extent with our filters that we use on our systems. So that's something that we're working on and we're doing. So a little status now because we haven't talked in a while. First of all, I'll tell you all about this guy in a minute. This is M22, one of your favorite clusters, Daryl.
Oh, yeah.
And the status right now is that this telescope here, we have a slight issue with the focus. Not so bad as you can see. We see it. Daryl and I know it's there. But we're going to get that fixed very soon. But the new camera is not the cause. It's actually it's the installation of the camera caused a slight mistake. And the camera's not aligned with north-south. So if I want to go up, the camera's going to go, the telescope's going to go that way, and south is that way. It actually aligns with these crosshairs very nicely. Okay, so north is up there, south is down there, and then we have east and we have west. Okay, so that's just, that's a really simple 30-second fix in there once we get in there. But that's the trouble with having a remote system, right? You just can't just say, oh, let me just go fix that. Okay, D. Smith is with us. Hey, D, how's it going? You know? And Cosmic Ray, you're a funny guy. You're very, very impatient, aren't you? That's okay. C&D Boy is with us. And the reason that I give a status like this, Ray, is because no one has heard from us in a while. And in case you didn't notice, we're also waiting for it to get to get rid of a full astronomical twilight, so it's fully dark out there. All right, so that's why I'm talking now. All right, because we're not ready to image yet without having rather fuzzy images with the red rings we've always seen from the sunset. All right, so cherry pomegranate flavored water. All right, so hey, Michael Hedrick's with us. Francis Palmer, hi, how are you? TNA Marc, you've been on TV in Canada every night for a few weeks. Awesome. Probably on the History Channel show, The Proof is Out There. I tend to do many of those episodes, I think. But hey, you know, people want to hear the science. They don't want to just have the fantastical, which I believe in. I just need data to prove it. And that's what we're working on, you know. Anyway.
Is the question?
Yeah.
Is that like History Plus or something? Because I've never seen that on History Channel.
Oh, yeah. No, it's regular History Channel.
And what's it called again?
The Proof is Out There.
Okay.
No, it's a regular show. It's not a show that's it's not a show that's that I'm making up, you know. Or a channel I'm making up. That's what it is.
I'll have to look closer.
No, I think you will. It's just regular History Channel, yeah. Alrighty. I don't know if you're looking for it now.
No, not now. I just I watch History Channel a fair bit, and I don't recall ever seeing it.
Don't know about the time frame. No, it's on though. Ask C&D Boy. Okay. So let's see now. Hey, Fantasy's with us now. Yeah, you have a good crowd very quickly tonight. I guess you guys have been really hankering for a good astronomy stream. Me too. Now, keep in mind, with the monsoon, almost every night was cloudy, and I tried to make it clear in the community message I sent out earlier in the week, that just because it's clear one particular night doesn't mean I can stream. Why is that? Because we also have to pay attention to the fact that this is a remote system. It takes time for people to get out there. So if they can't get out there right away that day, well, then the problem is that it might be a day delay, maybe a 2-day delay. So what if if something happens and there's a fault in the system? Okay, hardware does break down, things happen. I'm overly cautious. So even with the redundancies that we have, I do try to be very careful about streaming on a clear night when I know the next night could rain. All right, so I will err on the side of conservatism, and I will not stream that night. And it kills me. Trust me, it does. You know. All right, Cyclone has a question. Are ghosts and UFOs live have simulator intentions? I do not understand that question, Cyclone. Rephrase and readdress the question.
Fantasy had a question for you also.
Okay, what's Fantasy asking?
Up a little bit.
Oh, okay. I took an amazing exposure shot of the Milky Way, a shooting star. Just wondering if there's a way to eliminate the double stars. Double stars? What happened? Please explain that. All right. Let's just try an exposure while we're waiting for Fantasy to send this in. Let's do 12 seconds on this Measure 22 object. Measure 22, of course, is a globular cluster, an amazing globular cluster. It's in Sagittarius. To see where it is, we can go to our...
So it's just to the upper left of the top of the teapot.
Which is right here.
Right
Here's
there.
the top of the teapot, and there is Measure 22. All right. Now, the moon will be rising a little later. We're going to try to look at a few cool things. And we can even do that while the moon is up, because it's not going to be full anymore. It's going to be like a waning gibbous. So it'll still be bright, but we've imaged in a gibbous moon and gotten some really achieved some nice results. Okay, so that's where we are. Top of the teapot. And to back out and show you that, you can see it in relation to the Milky Way there. All right. So we're stuck in this part of the sky, and that's where the telescope's pointing, right there. Right? So, now let me just do one thing here.
Cyclone rephrased his question for you.
Oh, good. Thank you, Cyclone. You said ghost UFOs have similar intentions. Well, that was a statement, not a question, but I'll try to figure it out. Autocorrect, yeah. Is it like, do ghosts and UFOs have similar intentions? Well, we have to first define what a ghost is and what a UFO is. But I have had experiences I can't explain that show me that maybe what people experience as ghosts are actually parallel universe bleed-throughs, where we're seeing some parallel universe interdimensional things. And the concept of interdimensionality, it's getting darker out there now, that's good. The concept of interdimensionality is something that's actually not as far-fetched as it used to be, because we can actually see some physics that shows how that might actually work. In fact, my lecture that I do around the country now talks about the methodology by which UFOs travel, if they exist, if they're real. The only way they could be here is to use a form of interdimensional travel related in string theory, and that's something that we won't go into, but it is really interesting. Okay, Alicia says, Darlene was with me, but by the time I went, oh, look, it was gone. What was gone? I missed it. She must have said something up above. All right, well, she'll get back to us on that. Renee Cruz says, the James Webb Space Telescope. question, Mark. Galaxy universe intrigues me. Well, it intrigues me too. And Calabos is here. Hey, man. So good to see you. I know. So good to see us too. Yeah, no, we're good. I hate the monsoon season because it takes us away. All right, 12 seconds here, and let's start and see what we're gonna get. Let's live stack this. Okay, and clear our stack. All right, this is Measure 22. And what do we get? Okay, good so far. And let's do this. Yeah, the red, you know what that's from. We got a little sunset. Ooh, beautiful. That's pretty. Let's zoom this so we can actually play with it. Measure 22 is really pretty. Look at that. You know, if we use our very high dynamic range, we can actually resolve the center into the separate stars. See that? That's pretty cool. And then we can, of course, blast it. All right. But that's really pretty. Very nice.
I've said before that if Messier 22 was farther north in our sky, that it would rival Messier 13, the big one in Hercules.
Yeah, I agree. Yeah.
Beautiful globular, though.
It is. And we'll let this thing resolve for a little bit, and then we'll save it out to our server. And we're going to call this M22 for Measure 22. And it's a GC, Globular Cluster. Okay. Ray asks an interesting question. Have we ever seen Sprites, Blue Jets, Elves, lightning artifacts? Sprites are a very interesting phenomenon that occur way, way up at the top of the atmosphere. And when there's lightning in the lower atmosphere, sometimes you'll see a red spike or a cloud, like a expanding, like a little, like an hourglass shape up above the thunderhead, and that's literally almost in space. And that is what's called a sprite. I have never ever seen a sprite. I would love to.
Yeah.
Hello, Izabela. Hey, Sam S.
It takes a lot of planning to catch one of those things.
Yeah.
You have to be shooting over the top of a thunderstorm that's like maybe 200 miles away.
Yeah, you got to be in the right vantage point, just like you said. You're absolutely right.
Yeah.
It's got to be the right vantage point. Oh, it's so nice to see this snow. I'm just so happy. Oh.
Isabella's here.
Yeah, I mentioned I said hi, Izabela. You didn't hear me?
Hi, Izabela.
You didn't hear me. That's okay. Oh, yeah. Okay. All right, so we did 12 of these. And we're going to keep going here. Let's see what else we can do. This is right in the middle of Sagittarius. So as you can imagine, there's going to be lots of stars in here. All right. And that's beautiful. You'll notice some of the stars look a little bit orange. Some of them look a little white. I'm not sure the age of this globular cluster, but when you see stars that are orange and on their way to red, we might have some red giants in these globular clusters, because they're among the oldest stars in the universe, the ones that are in globular clusters, because they don't have a lot of elements in their spectra other than hydrogen and helium. And, you know, as astronomers, we call all the rest of the elements metals. They're not metal. Yeah, I know that. But basically, non-hydrogen, non-helium, basically all the rest are not in the spectrum of these stars in these globular clusters here. And that has to do with the reason that of the conditions under which they formed. They formed early on in the universe, and when they formed, there was only hydrogen and helium in the universe at that point, because there weren't supernovae to produce all these additional elements like we have in our sun's spectrum. So that's why these stars have a dearth of hydrogen. I'm sorry, elements other than hydrogen and helium. You know. Yeah, this is actually at 25% in terms of the size. So if I zoom out, you can see the full size of this frame. Okay, this is the new frame size. Measure 22 would be a third smaller if we're using the other camera. All right, so we actually are zooming in and we're using more pixels, so we're actually getting higher resolution ultimately out of this. All right.
Didn't you say recently to me that your new field is about 1.5 by 1 degrees? The old one was 2 by 1.5.
That's correct. Yeah, let's see if it's reflected here. Let's zoom into this here and see what it says here. Yeah, if you look here, it says it's 1 degree, 29.25 minutes by 59 minutes. So it's like 1.5 degrees by 1 degree now in size. See that? So that's the new field.
Yet the telescope is still working at f2, of course.
That's right. F2 with a now we're actually looking at a smaller patch of sky with more resolution than the previous camera. So what that does is when you're looking at a smaller patch of sky, it's zoomed in a little bit more, and you're using more data in the camera, you can zoom in further to see details. So this will allow us to capture galaxies and see galaxies that are just stunning. We'll be able to see a lot more detail in the galaxies with this. Yeah.
Marc Fantasy's asking about your email address he could use.
Oh, yeah.
He wants to send you that picture.
Oh, fantastic. Yes, you can send email to me if you want to talk to me directly. I should do that. It's the following address. Let me add an object here. Okay, we're gonna do this. I'm gonna create a new text box and give you my email. That didn't come out right. Okay. Email. MUFONanalyst@gmail.com. All right. There we go. Okay. So here's my email if you guys want to contact me specifically. This is the email you can use right there. And we're going to let this come in a little longer. All right. Oh, okay. Luciana's with us. Hello there. And Renee Behrens is with us. How you doing, Renee? Renee bought one of our cups, one of our mugs, our travel mugs. I think she liked it. She sent me a picture of her with it with a big smile on her face. I thought that was just the coolest thing. It's nice that people can be affected by what we do in a positive way. That's just really important. Sorry, hang on. It's not an earthquake. I'm just trying to fix my camera here. Get it out of my face. Here we go. All right. Okay, so this is coming out pretty. I think we've stacked quite enough of these. Really pretty. Okay, so what we're going to do is we're going to pause the stack here on 40 images. We're going to save it. And you can see we're saving it. There's our green save line, shows we're saving it. And then I'm going to save it exactly as seen. So if you just want to download a pretty picture, you can. All right. So now you'll see it's been saved as a PNG file. All right. So now what we'll do is let's go to our planetarium, back out a bit, and this time we're going to head over just toward the west a little bit.
Cyclone has a question of you.
Okay.
He says, are there any supergiant stars visible right now? And I was starting an answer, but Antares is the obvious choice. Antares is going away quickly, though.
Yes, it is.
It might already be too low.
Yeah, maybe. I don't know. I don't think so. But Antares is really bright, and we gotta be careful with that one because it makes these big halos. That doesn't hurt us. Okay? Let me get rid of my email. Copy that email, guys. If you want to talk to me, that's how you get to me. That's direct to me. Okay? So go for it. All right.
And Francis Palmer has a question of you.
Okay, Francis. And where are we? Oh, there we are. How far apart are the stars in this globular cluster? That is a fascinating question. That relates to how they interact with each other. And so when stars orbit each other, there is a natural order of things. So these stars, like if we were in the center of one of these globular clusters and we looked at the stars, everywhere we look in the sky, we'd see a fairly bright star. Not everywhere, but they'd be spread out almost evenly in all directions. And that would tell you that you're inside a globular cluster. But you'd see lots of space between them. See, it's an illusion because we're looking at this here and we're seeing things like a globular cluster with stars, but you're seeing the bloated images of stars that are 10, 20, 30,000 light years away. So, but stars are literally infinitely small points of light. Okay? And they do not look this big in real life. Typically, they're just tiny little points of light. And so if you saw them, you'd see light between all these stars, okay, that you see here. You'd see light in between all of them. You know, in other words, dark, I should say. You see the intervening darkness between them all the way through the cluster if you only saw just the brightness of the star as a pinpoint of light. But because we're using cameras, we get these bloated images because they're close in our sky. And then as the bloat continues, they overlay each other. And that's what happens when we look at a cluster like this. Okay? But, we sometimes do cloudy night streams using a simulator that allows us to literally fly right through globular clusters and the like. And you'll see that when you go through a globular cluster, you're seeing the stars as points of light. And that makes them interesting because when they're just points of light, you can see how you can just fly through and never hit one. I know it looks like you could, but you can't. Yeah.
I saw an explanation of this question a few days ago, if I remember correctly. It varies somewhat depending on the globular cluster, Francis.
Yeah, I never even answered this question, so thank you. Go ahead.
If you were in the center of a globular cluster, you might have 100 stars, 100 bright stars. If you were in a cube, 3 light years on a side in the middle of it, you might have 100 bright stars within 3 light years of you.
Okay, we're going to clear this. Yeah, and of course that spreads out as you go further away from the center of where you're located. When you move outward, you're going to see stars that are fainter and fainter and fainter. Okay, this is our night vision mode that you're seeing here. Okay, that's a shot. I'm going to change that. We want it to be a star 1 second shot, so we can actually move the telescope and you can see what's going on. There we go. All right, we're going to another one now, and this is going to be a beautiful nebula that is just a showcase. to showcase, and so we're going there because I got to show it to you. And it's only just a little bit west of here, okay, and you'll see it show up here in the view momentarily. We're going to go by the other one, and then here we are. So we're going to pull this one in. Okay, so in order to get to this one, we have to actually jog a little bit west, and you'll see that it's going to go in a weird direction. That's because we're on a diagonal, remember. We have to align this. And now if we go oddly south, then this is going to be pulled from here up to the center. Ready? Watch this. So now we're going to go south, and we bring ourselves to the center. That's actually one more jog and we'll be good.
And Cyclone has a question of you.
And Cyclone says, what program are you talking about? The program is called Space Engine. Now, we have the commercial version, so we have millions of stars that we're seeing at the same time. I have a supercomputer here, just to be fair. And so when I run it, it's smooth as glass. And you can do virtual reality goggles with it. And let me tell you, there's no finer way to get sick than to do virtual reality goggles with Space Engine. Especially when you're going over a planet and then you swirl around and then zoom through craters. Oh, yeah. But it looks beautiful. Okay. So now, this is the Trifid Nebula, and we are guiding now. You can see up above here that we have our guide. For those that may not remember, this is our telescope control. This is the telescope computer. This is the telescope, okay, in the building. I usually have another one behind me, but I'm in here now, so I'm not going to put it there. This is our main view, and this is the camera control cluster. This is the little bit of the image processing we can do, and this is the focus adjustment down here. All right, so let's do this. Let's now do a 25-second shot of the Trifid Nebula. Okay, it's really Trifid. So that comes down. We're going to get out of that mode, go into live stack, and get rid of the last image. Oh, I already cleared it. Okay, so now you'll see over here this yellow bar. This is our progress bar over there. That tells you how far along we are. When that fills up, you'll see an exposure appear, and you'll also see this get populated with our curve that shows our light curve. So check that out. All right. Hey, Papa Tom. Oh, look at that. That's just beautiful. That is the Trifid Nebula. Look at that. That is really pretty. Yeah.
Blue's on the left instead of at the top now.
Well, again, remember our issue, okay?
Yes, exactly. I
North,
know.
south, yeah. Well, for people who don't recognize, it's a good question to ask. Okay, so we're gonna let this one come in for a little while. I'm noticing this one, I went too soon. I'm gonna clear it because these stars are elongated. So we'll take it again. So how you doing, Papa Tom? There we go. Look at that. You can already see this camera is producing much more detail, Daryl. This is one exposure. And look at all the intricate detail we can see in here now. You can also see the red of additional nebulae. This is embedded within. It's just crazy. It's amazing. Okay. I'm going to take a sip of my cherry pomegranate water. Look at that. That's really interesting, Daryl. Look at the blue section. We could zoom in a little, probably.
I believe that's Messier 21 down to the lower left there.
The cluster right here?
Yeah.
Yeah. I'll check it out. And Francis asked if we could zoom in. Yes, we are. I had to let a few more come in. Wow. A little elongation, but we'll let it ride. Look at all this detail in here, Daryl.
Mm-hmm.
Previous camera, we couldn't quite see that because this was about as far as we could go in before it started getting bad. And we're only at 34% of this sensor. And we got a long way to go if we want to. But we have a little elongation. We got a little bit of wind out there. So I'd rather catch the majority of the nebula right now and not worry too much about the stars. That's really pretty. Cosmic Ray asked about the supercomputer. That supercomputer I'm using is a 6-core AMD system, Ray, with one of the better graphics boards in it. New power supply too, 900 watt power supply. No, 1,000 watts. I'm sorry. Up from 600. And it affords me the ability to do a lot of things way better, way faster. All solid state drives. A very low latency on everything. So, kind of it's as close to a supercomputer as a regular person can get, I think, and just have one chip in there instead of a lot of parallel processes running across many chips. But it's a 6-core system, which means that it's running much faster and splitting the time between 6 different cores, 6 processes, so to speak, that all run together. So basically, that's a lot faster. Yeah, Fantasy says crazy how cheap the SSDs are now. That's true. I bought one just to have it, and use it. It was like a 1 or 2 terabyte, and it was $50, $70. Yeah. Oh, look, you just said it. Okay. Okay. There's 10 shots here. I'm gonna save this, but I'm gonna change the name here. We're gonna call this Measure 20, which is what this is. I have not heard yet from the Grand Canyon. I applied to be a astronomer in residence for 2 weeks. I think I'll hear by the 15th of the month. Who knows? They might have a backlog of people, or maybe I'm not suited to the job. I don't know.
Would that be for next year at this point?
Well, yeah, it will be next year at this point, unless they have an opening and they want me to do like a December or something, which I don't wish on anybody at the canyon.
I thought that was a summertime thing. Here we're coming up on Labor Day at the end of summer.
No, they do year round.
Do they?
It's a year round, yeah. You'd be up there in a freaking snorkel jacket. I'll tell you what, though. When I did apply, I actually said no January, February, or March. I started with April and said to the rest of the year. But if they said January's open, I'd say, okay, I'm going. And I'll just suck it up for 2 to 4 weeks. It's a 2 to 4 week assignment. Now, because I have internet up there, guess what I can do? I can do this from there. Or I might be able to stream the talks I do for them. I got lots of talks I can do for them. Wow, look at this. This is beautiful. I'm really liking this.
Can you explain to Ray what the issue is with the camera? Not the orientation, but why
Ray.
the stars are blobs.
Well, right now, Ray, it's slightly out of collimation, so I have to. We have to go in there and work on that. And I've got someone that will go out there. Marianne will go out there. There's the Trifid Nebula, by the way, so you can see, got a name. But I'm not. They've been going out there several times to install the camera, to do cleaning, to do the bi-weekly maintenance. So I'm not pushing them to go out there right away, you know. Alicia's asking you a question.
No, I mentioned her.
Okay. Cyclone says, could you consider the universe to be an infinite fractal? Well, are you telling her about Ed Ting? Is that what you're saying?
Yeah.
Okay. An infinite fractal? No, I wouldn't consider it to be an infinite fractal. There's a lot of different models for how the universe is really laid out. That's the realm of cosmology, not astronomy or astrophysics, although we dabble with those models. Theoretically, if the universe is what we think it is, if you go in that direction for as far as you can, you'll end up coming back to the place you started. Now, let that work on your brain for a while. Yeah. All right, so I'm going to do 20 on this, and then we'll stop. I am going to make one adjustment to... It's just a slight wobble. I had a question, Daryl. I wonder if this guy right here is a little galaxy.
Just a second.
I wonder. Okay, so we're going to save the Trifid Nebula this way.
Can you point that out again now?
Yes, I will. I'm not using my on-screen stuff. I mean, I could actually. I could do this. Say, all right, well, I'm looking at, where is it? Where is it again? I saw it. Wow, I guess I'm looking for it again. Hold on. Oh, this right here. This guy right here. Right there.
The dim red one or the bright white one?
Let me zoom in. No, this one right here.
I don't know.
That might be a string of stars, actually.
We're looking through a very thick part of the Milky Way there.
Yeah, I think that's a string of stars. A line of sight thing. Wow. So, Ray, the answer was... the answer was that I don't consider the universe to be a fractal universe per se, but
that was a cyclone.
Yeah, I know, but Ray was making a comment about that.
Oh,
yeah, I was talking about this thing right here, Daryl. Well, now you can't see it because I just erased it. But inside there, but that I think that's actually a bunch of stars, to be honest. Okay.
Yeah, well, we're smack dab in the middle of the zone of avoidance, so...
yeah. Pretty close. Bad's window is a little bit down to the lower left here. Actually, no, it's actually a little more to the east, that way. And a little bit lower.
East.
All right. Yeah, okay, so we're done there, so we're going to save this again.
Bad's window would be southwest of...
southeast.
I beg to differ.
All right. Well, let's go back here. All right. So here is the Trifid. right? And
Yep.
we back
And
out.
then, Bod's window is off
Oh,
the
it's
tip
down.
out of the
It's
teapot.
down there, so it's more south than it is east. But it's south, roughly, right there. All right, excellent. Well, while we're in the neighborhood, we're going to explore other nebulae that are really cool, and we're going to go back to our night vision mode here, and we'll get out of this guy. Beautiful region, very, very beautiful region. And, you know, when you look at something like this without the benefit of a fancy schmancy camera, then you might see just a little hint of nebulous detail, but that's about it, you know. All right, so from this position, let's go down and just take a look at Herschel 36, otherwise known as the hourglass region of the Lagoon Nebula. It's the Lagoon Nebula proper, and that's just south, and so here we are. All right, so we just have to go south a little bit to pull into the middle, and so let's just do this.
Ray wants to know what the new camera is. CWO camera.
It's the 183 MC Pro, Ray. I'm thinking we might take some might actually do some more take some more money to do something else. Okay, let me go in here. Okay. All right, so we'll take an exposure here of the lagoon area, the lagoon complex. This is a good one. We'll do 25 seconds once again. We are guiding now. We should be good. And we'll go in and stack it and see what we got. There's the Trifid from before. That will be up on the server in moments, if it's not already. It's probably already there. Okay. Now. So hopefully all of you guys have had a good time over this holiday weekend. Ay, look at that. Now you can clearly see the difference in the size of this chip.
Oh, yeah.
Okay, so now let me, I'll
Wow.
back us out in just a second. Isn't that cool?
And that's just one exposure.
And that's one exposure, and there's more detail, more pixels in there than before. We could probably see the Bach globules a lot easier. Ray says you should piggyback another scope there. Well, actually, we already have a piggyback scope there. That's the guide system. But I would consider just doing a very wide sky camera that might even capture part of the observatory in every shot as we take the pictures, because the sky is just so stunning there, you know. And that would really be pretty too.
Just piggyback on top.
Yeah.
I did that a lot when I did astrophotography back in the day to film cameras. I just mounted the camera with a normal lens on top of the telescope and let it go along for the ride.
Yeah.
Catch entire constellations that way.
Oh, yeah. All right, so as I zoom out, you'll see the whole field now. If you recall, with our previous camera, the lagoon took up a space about this big. Well, maybe about this big. Okay, and now it's taking up almost twice that because it goes out to here, you know. So as you can see, we're capturing a lot of detail. And by the way, the two parameters, the exposure at 25 seconds and the gain, our gain is at 200. I normally run it at 300 or 250, and I'm running it a whole 100 less than normal. So we're still getting a lot of detail here. So, and that's because these are bright nebulae. If these were faint, I'd run it at 250, 300. And Izabela says, I love this, the closer view. You know, yeah, I know. It's beautiful. And we can zoom in and look at the... Now, again, these stars... I'm going to make an adjustment here. So let me just clear this as good as you may think it is. I'm going to clear this, get out of this, come back to our night vision mode for just a minute. All right. And I'm going to come over here and make an adjustment. Okay, we're going to go into our computer up here. We're going to adjust our correction rate in declination. And right now we're at 22, and I'm going to go to 23 and hit enter on that. Okay. And then back to our guide again. All right. Now we're going to try that and see if that works a little bit better. Doesn't take much.
Mark, will you excuse me a moment, please?
All right.
Be right back.
Sure thing. Okay, so out of this again and into the live stack again. It's really good to see all of you. Let me clear that because that's not what we want. That's an old one. Here we are. And Prow was with us. Hello, Prow. Thanks for coming out. And look at that. Marianne Robb is here. Cindy Murphy. Hey, I heard you. I saw you before and I didn't say hi. I'm sorry. Okay, that didn't work. I think we got some wind blowing us around. I could tell by looking at my numbers up here. Correction to 3.8. So you want something that like 6.5. That's like a huge amount. Right. So that looks pretty good. But it was doing 6.5 while I was taking that exposure. That's not good. Yeah, we're getting, like I said, there's a little wind happening right now. 0.9 and 1, that's good. See, those are really good corrections. If they're, under 1.5, I'm going to predict that this exposure will be a good one. Yeah, see? Okay, this is the one coming up. Looks like 1.5 was the highest we saw there in the correction here. All right, that's good. 2.2, 2.4, 3.1, 4.9. Uh-oh. 7.2. Oh, boy. Yeah, this next one's going to have a little elongation built in. Yeah, there they are. Okay, well, we just have to weather through the weather. So we'll clear it now. And so what will happen is the telescope has a guide star, and if that guide star moves too much, it won't be able to keep the guide star locked in, and so it has to recalibrate. So this is going to be a bad one too. So we'll get out of that and let it just calm down. To the victor goes the spoils, right? This one might be okay. No, it was blown around too much before. All right, we'll keep trying. We just have wind coming in, and it's this front end of the telescope's acting like a sail, and it's just being pushed around. I didn't see all the numbers, but those look good so far. Yeah, that's good. All right. These numbers are looking good. Looks like the wind calmed down at the moment. Oh, 2.8. 3.0. Okay. That's brief. We might have eked this one out. Let's see. Okay, that one worked. Yeah. 3.4, 3.5, 4.1, 6.1. Okay. 8.5. Holy cow, we got a lot of wind out there. Okay. Well, we'll just have to live with that for now. If I pause it, well, it's probably it will have already been doing that. So if I wait for it to calm down and unpause and resume, I think we'll be good. But we're getting the wind. You can see that right there. See, when it says searching over again, it means that the wind is blowing the telescope a little bit too much. It is capturing, but it's just not putting it on the, it's not reading it off the sensor. All right, so we'll say resume right now. Okay, 0.9, 0.7. You want it to be under 1 if you can ideally be under 1. Okay, this one looks like it's going to be good. This will be a good one. Yeah, see that? That's a good one. Okay, that one looks good so far. 2.9, that's a little high. 3, 3.3, 3.6. Okay, pause. Yeah, 7.7 loses its star. That would have been an elongated one. So you see how we're riding it? I'm just sort of... It's like we're enforcing the guiding, you know? We're getting wind out there. I think you're back with me, Daryl?
Yes.
Yeah, we're getting wind. So what I do is I pause it when I see the numbers go too high. Right now, they're up to, you see like this, they're like, they're pretty good actually. So if I hit resume, this next image will be good. Okay, there we go. That's a good one. So if I watch those images, if those numbers climb to above 2, then we're not good. We gotta pause it and let that image pass. It's like we're weeding it out dynamically. So that's 2.1, 3.3, 4.3. Okay, we're gonna pause this. Not gonna keep this one. Don't want to ruin the image we have so far. Let's see what this does. And we can just start it up and just stop it if we want. Yeah. Anyway, looks beautiful though, doesn't it?
It does.
Yeah, this is really pretty. Really pretty. Oh. I forgot to tweak it. We're good. Well, you know what we'll do? I will save it just like this after I label it. This is Measure 8 Lagoon Nebula. And we can try that one and save it exactly as seen. Little satellite went through here. You see that? Where's our Lagoon Nebula? Put that down a little lower. A little lower. There you go. All right. It's really pretty. Let's zoom all the way out just to see the rest of the field. And now let's try a little processing here.
Michael H., not to jump on you're addressed to Marc. From a dark sky, yes, Messier 8 is naked eye visible. This
Yes,
is one
like
of
the
the
Orion
objects that,
Nebula.
I'm sorry.
I like the Orion Nebula.
Yeah. This is one of the objects that the ancients actually knew. Naked eye.
Wow, that's really pretty. Well, let's zoom in a little on that. Wow, look at these beautiful dark tendrils in here. These are just beautiful. And let's see now, if we put the unsharp mask on, yeah, of course it makes that brighter, but it also enhances these beautiful tendrils in here. This is literally a lot nicer than the previous camera. If I turn this off, it won't overdo this little guy right here. This right here, that bright star you see right there, that's an O-type star. And this is the hourglass feature of the Lagoon Nebula. And that is the star that's powering much of this nebula. There's other stars, a young cluster here, of course. And their stars are also contributing. But the O star here can use its ultraviolet radiation because most of it is ultraviolet this star is giving off. So it goes out in all directions, and it causes ionization of the hydrogen gas all throughout this region of space. And that's why it's a roughly spherical area around this star, right? Because, but the distribution of hydrogen isn't even, so that's why it looks sort of like a nebula. It's all over the place, and it's also filled with dark nebula, as I say, dark dust that is silhouetting or being silhouetted by the brighter gas behind it. All right, so it's pretty neat. It's a gorgeous location. This is this right here. This is birth in the universe. This is where supernovae star will come. Will litter nebulae like these. It'll populate nebulae like these with this dark dust and more of this gas. Elements beyond your wildest dreams that are all in the periodic table come here and are part of this process of star death when stars blow up. And it's from those debris leftovers from stellar supernovae that stars form and planets form from them, because this dark dust becomes aggregated into planets eventually, and the gas in here, the hydrogen gas, becomes stars. And the gas is also filled with calcium and potassium and phosphorus and magnesium and iron and all these other elements that are in the periodic table that happen to be in this particular region. And thus, when the star forms, it forms with those elements in its outer envelope. Its core is going to fuse hydrogen into helium, all right? And as the star gets hotter and more massive, it may actually develop into a star that's going to be fusing hydrogen so fast into helium that it's going to quickly go from fusing hydrogen into helium to fusing helium into carbon and beyond. And so the star's evolution is very quick. And stars like this one right here, like this O star in the middle that's powering a lot of this nebula, O stars like that, they live just a few million years. Unlike our sun, which is living 10 billion years. So it's many orders of magnitude shorter lifespan. And they're not really alive, you know what I mean, existence. And that star we're pointing at right there will eventually go off in a supernova that's going to create a beautiful nebula within a nebula here. So you'll see a supernova remnant inside of this nebula, and that's really amazing. So, anyway, there we go.
If you remember when we looked at the Rosette Nebula before, it's no coincidence that the lagoon is reminiscent of the Rosette or vice versa.
Yeah. Now, the thing
similar things going on.
Yeah, and the thing that's happening here is, this one hot O star in here is somewhat clearing the path in here, somewhat making an opening in here, what we call a cavity, making a cavity around itself. Its stellar winds so strong, pushing out so much that a lot of the dust and gas are pushed away outside, and so it tends to open up the area around itself because of its high radiative output. And that's what we're seeing in things like the Rosette. It's a whole cluster of stars doing that. In the Lagoon, it's that one O star, which is actually forcing a lot of the dust away. I don't know for sure, but this curved nature could be due to the fact that this O star is pushing the stuff away, and of course, as it goes away, it forms a curved arc. You know, it's very possible. I'm not sure how likely, but it's possible. And Marianne Robb is saying a big thank you to Robin Curtis for all her wonderful volunteer work with STLS products. I second that, Marianne. You're absolutely right. Robin has been amazing helping us create products. So show Robin some love, folks. She really deserves it. And we're going to get rid of this now and look for something else. All right, so this guy here. Let's go back to our night vision mode, or we can call it our enhanced vision mode. All right, and now we're over here. And so we've done Measure 22, we've done Measure 21, Measure 8. Should we do the Pillars of Creation? What time's moonrise tonight?
Give me just a second, I'll find out.
All right. Okay, we're going to go up to the Pillars of Creation. You're familiar with this particular object that the Hubble Space Telescope captured in an extraordinary way. And now I'm going to see it for the first time with this new camera. Good night, Fantasy.
Moonrise is in about 8 minutes.
Okay, so it's about the 9:18 p.m.
9:18 Arizona time, yes.
Yeah, okay. All right. Well, we're good. All right, let's just go a little bit to the west here. Bring that down in here. Okay. And then we're going to go a little bit to the south. Bring that toward the center. There we are. All right. And we'll set up. We're going to do a 25-second shot. We're already getting moon glow on the horizon, I'm sure. Okay, let's see if we're going to stay stable with our guiding up there. 0.8, 0.3, 0.2, 0.4. I'm liking it. We'll go for it. We want those numbers to stay low. Okay. That's our beautiful Lagoon Nebula. All right. All right, let's go. Stay under 2 and we're golden. Okay, let's go to here now, our histogram. And this picture will be good. Oh, look at that. Holy cow. Look at that. Look at the Pillars of Creation, guys, right there.
Yeah. I think with the increased image scale, the pillars or the eagle does stand out a little more.
It will. In fact, I'm going to drop it to here just for now, just to look around. But this looks pretty. So we could zoom in on this a little bit more. Look at that. That's really nice. That's just 2 exposures. Let's see what it wants to do. It's going to do a little brighter, a little darker, like that. Okay. Wow. This is really nice, guys. Pillars of Creation right there. Let's color correct to see if we can get that color. There we go. That is really nice. Darlene is off to sleep. Hey, you know, life is hard on a 9-year-old, you know. All right, Darlene, good night. And Alicia's going to hang with us for a little while.
Can see the prairie a little bit also.
Over here, right?
Yep.
Yeah. I just want to make a public shout out to Alicia Vieras. She's Darlene's mother, and she's been exposing Darlene, her young'un, both her and Donovan, her husband, to the most incredible brain growth stimuli ever, you know, with astronomy and science and so forth. And Darlene's interested in it, and hopefully she'll stick with it. But I can say this, watching how they've raised Darlene, everybody should take a lesson from them, because she is such a well-balanced kid. Now, if I'm wrong about that, Alicia, you can correct me, but I think she seems to be pretty well-balanced, and she gets that from her parents. I'm convinced of it. And I believe, Renee, aren't you her grandmother?
I think she is.
So that's...
I caught that conversation earlier in chat.
Yeah. Okay, I didn't see it. But I mean, I think she's grandma. Oh, Alicia, that's fine. You deserve it. She was just saying, oh, thank you for that. That's fine. I call it like I see it. You know what I always say, Alicia, and to everybody? When you're talking to a child, you never know who you're talking to. You could be talking to the next Einstein and not even realize it. You know? So you gotta be conscious of that fact and treat them as if they might be. And then that gives them the confidence to look into things on their own, ask questions when they might just be quiet because they feel embarrassed to ask. Man, I've seen that a lot. No need for that. You know, no need for that. Oh, yes, Renee's Native American. That's right. And I remember telling Renee at the conference, my mother was Native American and Irish. And so I've always been surrounded by Native American culture and so forth. And to me, it's not even a big deal to me. It's just sort of like, well, it's almost like, well, isn't everybody? You know? Oh, by the way, Mr. Django, I forgot to say hi to you. How you doing, man? How are things in Belgium? Hi, Gladys. Yeah, I want to be the next Bill Nye the Science Guy, Gladys. I just don't want... I'm not going to do it with any politics. I think science doesn't belong sticking its nose into politics.
I agree absolutely.
Yeah, science is science, and that's where it should stay.
Yeah. I could say a whole lot more, but I'm not going to.
No, because I'll mute you. I'm kidding. Look at this. These are beautiful. You know, once the telescope's collimated, these stars are going to be perfect pinpoints. And but even like it is, it's actually pretty good, Daryl. I'm really pleased with how it's performing in spite of itself right now.
Oh, yeah.
I really love the size, too. Let's just, for fun, let's zoom in more and see. Okay, this is... Yeah, see, you can see how now it's looks like it's a little out of focus, right? But that's, again, that's part of the collimation process. Because if the stars can't get much smaller than that because of the collimation issue. So,
did I ever tell you?
That's a good idea, Ray. Did you ever tell me what?
I got into it with Bill Nye on the radio one night a long time ago.
Oh yeah.
Yeah, uh, he was Bill Nye, the up and coming science guy uh, at this time. It's long ago, before he became famous. Really, he
Mm-hmm.
was still calling himself Bill Nye, the science guy.
Bill,
He
Bill,
was on a
Bill,
late
Bill.
night program on a Denver radio station one night, and I listened in, and he wanted to talk science. The host of the show was she was not well versed in science, and the people calling him with questions, they all wanted to talk about pyramids and stuff like that, you know.
Mm-hmm.
And I called in and started talking astronomy and little light astrophysics and stuff, and he didn't know what I was talking about.
Really?
Yeah, I mentioned Olbert's paradox in particular, and
You didn't know what that was?
ooh, no, he didn't. He had no idea.
Oh wow.
So I aced Bill Nye on the radio one night.
Well, for everybody listening, if you don't know what Olber's paradox is, it's this. It's if the universe has as many stars as we say, technically you could look in any direction and see a star. So how come we don't have a sky that's just white with stars? There's a number of reasons why that's the truth. I mean, truly you are seeing a star in every direction you're looking. But it has to do with the fact that they're not as bright due to many reasons, like right here, dark dust in between us and the stars, or the fact that the star's light is dimmed by the square of the distance the star is away from us. So if a star is 2 times further away, its light's 4 times dimmer. If it's 4 times further away, it's 16 times dimmer. And that's called the 1 over r squared law, or the law that dictates how bright light is, and how it attenuates or dims with distance. So Olber's paradox doesn't hold true for a variety of practical reasons. Dust, dimming of the light by the 1 over r squared law, you know. So there's a whole bunch of reasons why Olber's, it's Olbers, Olbers, for those who want to look it up. So, neat.
Well, Olbers posed his question over 200 years ago, if I remember correctly.
Yeah.
And they didn't have the understanding we had now. He reasoned that if there was a star everywhere we looked, the entire sky should be as bright as the surface of a star.
Yeah.
And because we didn't see that, what did that say about the universe?
Exactly. Okay, this is pink, the Eagle Nebula. That's Messier M16. So we did M8, M20, M22, M16. Charles Messier spent a lot of time in this region of the sky.
He had help.
Hey, Skillski, how you doing?
Pierre Machine,
Yes, he did.
and
Man.
Herschel.
Mm-hmm.
Herschel the Elder. He contributed some to the list also.
Now, if you look at this, even with the collimation issue, look at the modeling in this area of this nebula. We're going to end up with some really fascinating shots with this camera. You see what I mean? Look at that. And your fairy over here, Daryl, is fully fleshed out. And again, we're only at 200 gain. you're seeing this at 300 gain, and we're going to be, 20% brighter, because this will all be filled in. There's actually nebulae all around in here, and if you notice, you're starting to see this brightness. This brightness we're seeing here, that's moonlight that's interfering already. We can try to get a little bit of it out, but maybe this way, and then this way. Yeah, but look at that. It's crisper and clearer in there. This is beautiful.
It is.
All right, so this is 27 images with moonlight. We'll save it exactly as seen. Very nice. Okay. And we can get out of our stack here. We'll delete it in just a little bit. And now we'll go back to our single frame. Wow, that was pretty cool too. Clara Mertens, how are you? Clara, this object, if you're talking about the object, that object we're looking at was this right here. It was the Eagle Nebula, Messier 16. It's a amazing stellar nursery area, and we spent a lot of time looking at nebulae and galaxies. And this is what you're seeing on the screen overall. This is SkyTour live stream. This is live observatory. I'm in Connecticut. The observatory is in Arizona. I'm running it from 2,500 miles away. And the observatory is right there. You see the telescope right here. Okay, the building here, the roof went off. And away we go. And we're actually bringing you the universe live in real time. And with an attitude, too, because, we believe that science is for everybody, Clara. So hopefully you'll hang around, subscribe to us if you want to, check out our store, join the Patreon if you want. We really enjoy what we do. I'm a professional astronomer. Daryl's an astronomer. You can hear him in the background. He doesn't like to be seen on camera for some reason. I think he's afraid the flying monkeys will get him or something.
Something like that.
Yeah.
I have a good voice. I have a good face for radio.
Well, it's all right, Daryl. Okay, so let's go now. And this is our planetarium view. This is a live view. Not a live view. It's a program that actually connects to our telescope, operates our telescope as well. So what I'm going to do is I'm going to ride up the Milky Way here. We're going to go to some other places. This is through Aquila the Eagle. And if you want to know where the eagle is, well, I can just pull up the mythological characters of the eagle, and you can see the eagle.
I hate that.
Yeah, it's not the right. It's not right. Yeah, I know.
Altair is the eye of the eagle, and
yeah.
Little star
These are
to
the wings.
Right, the top of his head. Those are the wings, and that's his tail at the bottom.
Yeah. They didn't get it right, but you know what? It's okay. It's okay because it helps people see what they're looking at. Okay, now I'm actually going to go up in here because the title of tonight is the stellar birth. Birth and death in the universe. So we just showed you nebulae where birth of stars and nebulae and most likely planets is occurring. And now what we're going to do is we're going to go to this other location. And this
Ray wants to see Cygnus.
Yeah, I know, right? So we're going to go to a new spot that shows death in the universe. All right, and you'll see the telescope is heading up. And it's going to stop right about there because that's about where this is relative to its view. And you'll see right now, as it pulls in here. Let me see if I can. Okay, now the moon is out. and it's going to hamper us a tiny bit, but don't forget we've got these filters. It might be 52 Cygni right there, if I got it right. Let me go back and look and make sure. Let's go here. Let's zoom in on this. And we're using Starlink, so sometimes we have some data dropouts. There we go. Yeah, that's 52 Cygni. Okay. So, we're going to look at this nebula here and see how much we can see of it. We may not see any of it. I'm trying to see what we're looking at here. I'm going to increase by 50. I'm going to increase our sensitivity here. I wonder if we might actually have missed it. Let's find out. Okay. Let's go into our stack again. We don't want that one. That's the previous one. Eagle Nebula with the Pillars of Creation in there. So we clear that buffer and wait for this next one. Okay, it's right there. So we're catching a piece of it. So I have to head north a little bit. I'll do that. The colors of this are stunning, and even in moonlight, you'll be able to see it because, like I said, our special filters will really show it to you in a way that you've just never seen before. All right, so what I'm gonna do now is I have to go west a little bit. Okay. I think that might be 52 Cygni. Okay, that's good. Now we're going to go south just a little bit. Okay. All right. Now we will... Let's do this. Let's go to our 1 second shot here because we were off a little bit. We were only at 4 milliseconds. No wonder it was so few stars. Okay. Yeah, here it is. You can see it there. It's a gentle arc. All right, we're locked on. We're guiding. And so what we're going to do now is we're going to do a 25-second shot of this guy. Actually, we'll do 20 seconds. We don't need 25 seconds. This is bright enough. All right. And then we'll get out of our night vision mode, go into our stack mode. And what is stack mode? I mean, stack mode is a very simple thing when you understand it. We take a picture, and then we take a second picture, we align it with the first and stack it on top. And we keep stacking this data on top of each other, make an image sandwich, so that all the dim stuff ends up coming out brighter, and all the dark dust and so forth that might be in there is all, oh, look at that, it's beautiful, is then going to come out even brighter. This orientation actually shows that whole segment, which we didn't have last time.
Yeah, it does. It took the words out of my mouth.
Yeah, it looks good. And is Bonnie with us? Yes, Anahata77.
Hello, Bonnie.
Hey, Rascally, how you doing? Very good.
Pity you don't have a rotate feature.
Actually, we can't put a rotator on this, but the new telescope is going to have a rotator.
Yeah.
And what's a rotator, guys? A rotator is such that we can actually rotate the camera, automatically, robotically. We'll be able to do it to take full advantage of the size here. So you see, this is the east or the western side of a supernova remnant, and it's a little bright, so we're going to actually click that down, show you the colors, color correct it to bring out the reds. Look at that. That's the real colors right there. That is beautiful.
Rotating would help you compose the image,
Yeah, you're right.
Just the orientation just so. We've talked about this with Andromeda Galaxy before.
Oh, sure. Yeah, we have.
You could get it long ways across the diagonal to try to fit it all in.
Actually, with this particular orientation, that might actually... Well, actually, no, it won't fit in. It's several degrees across, so we're going to see more detail in galaxies like you can't believe.
Yeah.
So, there we go. All right, so now, what are we looking at? Well, that's this. Let's move that around. That's the Western Veil supernova remnant toward the western side of the sky.
Also known as the witch's broom.
Exactly so. That is right. That's right. The witch's broom. And let's move it down just a little. And let's darken it up a little, which will enhance the colors. Look at that. Wow. Telescope is guiding great. You'll notice the numbers here. These numbers being under 1 are perfect. We know when there's a good exposure coming and when there's not. So right now the wind has calmed down out there. And the telescope in this position, like you see right above me, that's the biggest flag it could be. I mean, that's really, really big. So it would be stuck up into the wind. That's really pretty. I'm going to take this down a little bit. And come back up slow. There we go. Look at that. That's nice. Okay. Cindy, thank you for that compliment. Alice Cooper, hey, how you doing? Go ahead, Darren.
Alice, when we look up in the sky, everything we see is spinning. Some spin fast, some spin low, but I would have to guess everything or practically everything is spinning. And that's all conservation of angular momentum.
Yeah. And actually, it comes down to the fact that everything in the universe has a frequency. What is a frequency? A frequency is how much vibration is being done by an object. And that's what you see when we look at this right here. You're actually seeing what could be for this. You're actually seeing what could be the result of electric currents generated by this supernova remnant. Where did the supernova occur? It occurred down here well past my head down this way in the sky. And this is something that's moving outward like this into the universe, right? And as it does, it's impacting other particles, and as it hits those other particles, other atoms out there of material, it's heating them up to millions of degrees, causing ionization. This greenish blue, this greenish stuff, this is oxygen, and the red is hydrogen, all right? And it stands to reason because oxygen and hydrogen are among the most plentiful elements in the entire universe. Okay, you've got hydrogen, you have helium, and then the next most plentiful element in the whole universe is oxygen. All right, and then the next after that, guess what it is? Carbon. Carbon from what you're made with. Okay, so the hydrogen and the oxygen stand to reason that there are going to be a lot of red nebulae, because that's what ionized hydrogen looks like, and a lot of greenish nebulae, which is what ionized oxygen looks like. So that's what it turns out to be in the universe. So, and that's kind of an interesting, I guess, thing to understand and follow. Because when we look at the abundances of elements in the universe, you know, the periodic table, that thing you hated in biology class. I can sing the periodic table. I know, there's hydrogen and helium and lithium, beryllium. You know, I'm not going to go through it. But it's how I actually learned the periodic table, is I put it to song, thanks to another group, too, that did it. And it really does help you. And it's fun. But if you look, right, you see these tendrils in here? These are twisting, twirling like tendons in a body, but they're just tentacles of gas, like up here. This up here, look at how convoluted that is. Daryl, like it's just like a tornado, like it's twisted. It could be a twisted thing, or it could just be a sheet of material like this that's edge on. Remember, the universe is in 3D, so we don't know how far in it goes. So it could be from the side, it could look like this, and then what we're seeing is edge on. We don't know, okay? But still, these tentacles, there's dense strands here. These strands that you see here are very interesting because it's those strands that could have developed from shock fronts, where the material is pushing out and hitting other stars and material in interstellar space, and heating it up and making it do what we see. Or it could also be that because it's striking other particles of dark dust, that electrical currents are generated by those interactions. That happens too. We know that. And those electrical currents could also be responsible for shaping this nebula, just the way we see it as it's expanding out. This is a new young science when we talk about electrical charges in a supernova remnant. So expect to see more of this. Okay, expect to see more of this. And now, not to forestall any questions, but when you talk about life in the universe, the question becomes, well, why can't other elements support life too? Why are we carbon based? Can't we be silicon based? And we can't be magnesium based or anything like that, because it has to do with the number of electrons we have available. And in carbon, you have 4 beautiful electrons just in the valence. It's called the valence shell. And the next most likely element that could do that kind of thing is in that column. And what's below carbon? Silicon. That's why people say, oh, silicon-based life. Okay? But silicon is very tenacious. It makes really, really strong bonds. And silicon bonds don't like to be broken. Right? What's an example of a silicon bond that everybody knows? Every time you walk on a beach, you're walking on silicon dioxide. You're walking on a silicon atom bonded to 2 oxygen atoms. So one thing I always say, keep in mind, it's kind of interesting, okay? But keep in mind that when you're walking on a beach, 2/3 of the atoms you're walking on are gas, which are oxygen. You can use that, no charge. Michael Hedrick suggests NGC 891, and I know he suggested that. That's a silver sliver galaxy?
Silver dollar.
Um, it's not known as a silver sliver also?
I believe it's a silver dollar galaxy.
Okay. All right, so we've got 29 here. We're good here. We got 30. So this is good. And I will change this name to Western Veil SN Supernova Remnant, SNR Supernova Remnant. And we'll save it now. And again, with the moon out, it's going to have a little bit of lightness to it. But trust me, the fact that you can see all this subtle dim detail is pretty cool. Let's pull that out. We don't need that name. Okay. Let's back out a little bit more now to show you the whole extent here.
Actually, I think I goofed up. I was thinking of what's the big galaxy? Where is it?
Oh, 4565?
No. It's a little farther over in the south, maybe in the fall sky. Fornax, I forget.
Oh, is that the not the Sculptor Galaxy?
Yeah, Sculptor. Okay.
Okay.
Yes,
So
that's what I was thinking of. NGC 891 is in Andromeda.
Okay, and that's a silver sliver, right?
I still don't see Silver Sliver. I'm looking.
Okay.
Yes, it is Silver Sliver.
All right, good.
Outer Limits Galaxy.
I'm not losing my mind. Okay, we save this.
It does look very much like 4565.
It does.
Edge on
Okay.
unbarred spiral galaxy.
Mm-hmm.
It's in Andromeda.
Okay.
It may not be very high yet. It's according to his numbers, it's less than 20 degrees elevation.
Yeah, we're not going to be able to see that. Okay, so what we're going to do now is we're going to head to the east by a little bit, and the stars are going to go to the upper right in this case, like that. And in so doing, we're going to bring in the next segment of the supernova remnant. And let's see how close we get. I may not have gone enough. Let me just come back in here. Yeah, okay, so we want to go to the eastern veil. Yeah, we gotta go up a little bit, yeah.
I'm a bad astronomer.
No, you're not. Okay, so let's go
All
north
this stuff
again.
starts looking alike after a while.
Nonsense. Nonsense. We're good. Alright. Let's try this and see where we are.
Question is, what galaxy was I thinking of?
The Sculptor Galaxy, I thought.
Yeah, I'm thinking like the NGC number though.
Yeah. I'm going to go to this star first because I want to... the telescope alignment's slightly off, which is not a big deal. I can do it on the fly now. And that was the star right there that we want.
I was thinking of NGC 253, which is the Silver Dollar Galaxy.
Yep.
Constellation Sculptor.
You got it. So we're going to go west now. Bring this star in. Okay. And now this star, I will bring up my crosshairs to just do the proper matching here. A little bit west. A little bit west. And that should pull it right in close enough to my crosshairs to then lock it in and synchronize it. Okay, so now we go here, and you'll see a difference from where the star is and where the telescope thinks it is. And that's what I'm going to change now. So we come in here, and I will now make sure the crosshairs and the telescope are in sync. So now, when we go and look at this object up here, we will be right dead center on it. All right, here we go. Off we go. And I can come in here and get rid of this guy. Okay. All right, I think I see it here. I'll be anxious to see what this looks like. All right, let's wait for our guide star. See, it says searching, waiting for the guide star to come in. Then we'll do a 25-second or 20-second shot on this. We don't need 25. And that's the exposure over here, and then the gain is going to be 250. We are guiding successfully, so let's get out of this and go into a stack and take out the last one we saw, that beautiful object which is up on the server right now. We'll clear it, and this is the western veil, which is a supernova remnant. So we'll just change this here. Sorry, eastern veil I meant. Eastern veil, supernova remnant. There we are. Wow, look at that thing. That's really pretty. Wow. That's the left side. On the right side is that other spindle you saw. And we've done mosaics where we put them all together. And it's stunning.
He's facing down now.
I know he's looking down. When I say he, and when Daryl says he, we're talking about, it looks like Alfred Hitchcock from the side in a sense. You can turn your head a little to the left.
Yeah.
And it's like a nose and a face and a mouth. It's just silly. We're being silly astronomers.
Can you back out a little bit?
Sure. That's about it right there.
Yeah.
Now look at it. Look at how gossamer this stuff is down here. I don't know that we saw that with the last camera. I think we did, but I think the view is superior to the last camera. And you know, when we do the professional processing on this, guys, it's going to end up looking really, really nice. You know. Ray is saying he's seeing some wiggles in the RA during slewing. That has always been the case with every single telescope I've had, every Meade telescope. They all do that stair-step pattern. In other words, they don't just move one direction; they move up and over, up and over, up and over, up and over. So that is a weird way in which they slew or move fast, guys. That's what we're talking about. Oh, Robin, thank you for coming. I'm sorry you got to go, but thank you so much for everything you've done for us. Yeah, this and once we get the collimation set up on the telescope, holy cow, there will be no stopping us. No stopping us at all. So everything we saw was birth in the universe, and now we're seeing death in the universe. This is the result of a star that has gone through several phases of evolution that resulted in a final cataclysmic explosion called a supernova. Okay, and what's left behind will be either a pulsar, a star that's rapidly spinning, like a rapid core of the star left over, a neutron star, it's called, with bright hot spots that swing out in our direction and sweep by us like lighthouse beacons in space, and so the name pulsar derives from that behavior. Or it could be something totally invisible, a black hole. And black holes are the most most mysterious object in the universe. Very mysterious. We don't know exactly what's inside a black hole. We don't. But black holes are giving up their secrets slowly but surely. Slowly but surely. So, when we talk about how a black hole operates and so forth, we would have to discuss with you how it's made. And at some point, I think we'll talk about that. We'll go through that, and I'll do that. I know we've talked about it on our radio show. Daryl, you remember the episodes we've done where we've talked about black holes, neutron stars, pulsars, supernova remnants, FRBs, fast radio bursts, which are really strange objects that seem to be coming out of very, very highly magnetic neutron stars called magnetars. The magnetar is so powerful that just its magnetic field would rip your atoms to pieces if you got within a few million miles of it.
Prowl
Michael
says,
Hendricks. Go ahead. Sorry, go ahead.
Prowl asks, how do we know that is from a supernova?
Oh, we can tell why things are from a supernova based on their spectra. First of all, when a supernova occurs, it occurs because a star has reached a certain point in its evolution, as I mentioned. And that certain point in evolution takes it through several phases. Among them are the hydrogen to helium burning, okay, the hydrogen exhaustion, where it runs out of hydrogen and the star bloats into a red giant after that, and then the helium burning, which allows the star to fuse helium into carbon, and that makes it get just a little bit brighter and turn a little bit more blue. And then when the helium runs out and the star starts burning other elements to fuse other elements, we start to see in the spectrum, we see not just carbon, we'll see neon, we'll see silicon, we'll see iron isotopes as well. And now the star, again, reaches this stage in its evolution where the fusion material that it can fuse, all the fusion energy or fuel, is gone. And so the outward pressure is the only thing holding the star up. So when the star's core stops producing this massive, unbelievably impossible to imagine force outward of radiation pressure, the massive weight of the star trying to fight its own gravity to stay up, gravity wins and it collapses. As it collapses, all that material goes down into the core, hits the core, which is iron, okay, and nickel, isotopes of iron and nickel, and then it rebounds off and blows up into a massive supernova. The process is a lot more involved than that, but the end result is that when you look at the spectrum of the stuff we see coming off, we see certain isotopes of iron, we see certain isotopes of silicon, and so we know that it was a core collapse supernova that we're looking at. So it's the spectrum which tells us a lot about what actually happened there. Okay. And Daryl just fell off his chair. So what was that for?
I'm awake.
You didn't like me answering that question?
No, I'm the one who posed it to you.
I guess so.
Something fell off my desk here.
That's fine. So that's why we know things are supernovae. Now there's other types of bursts as well. There's supernovae. There's nova. There's a nova as well. Novae, regular novae. And there are other types of supernova that destroy the star as well, known as type 1A supernova. This was a type 2 supernova. This is a core collapse supernova where the whole core collapsed in the star and blew outward. But a type 1A supernova is a different supernova. It occurs when you have two stars that are orbiting each other. And guess what? That's a relatively common occurrence in the universe. And when one star evolves past the hydrogen burning and helium burning, if it does that at all, swells into a red giant, and then it shrinks down to a white dwarf. When nothing else can happen, it won't blow up. It's not massive enough to blow up, and so it becomes a white dwarf. And now you have a white dwarf circling a normal star. Okay, like with the star Sirius, there's a white dwarf that's circling Sirius as well. Okay, and then and lots of other stars. They're very common. Now that white dwarf, we know a lot about white dwarfs. White dwarfs are about the size of the Earth. The sun is about 1 million miles across, and it's not a very big star. It's an okay-sized star, but a white dwarf's only the size of the Earth. All right, and the Earth is 8,000 miles across. So take that and imagine now that this white dwarf is now orbiting. A white dwarf is very condensed, very, very dense. And it's a white dwarf because it hasn't reached a certain critical mass. If it's a little bit higher in mass, then it might have become a neutron star, where it might have shrunk further into a neutron star. But that mass isn't there. And that special mass number was created by Subrahmanyam Chandrasekhar. He figured it out. It's 1.44 solar masses. Now, that's the core. The star could have been a 10 solar mass star, but the core might be less than 1.44 solar masses left over. And if it is, well, then it'll be a white dwarf rather than a supernova. All right? So that kind of thing is very important to follow, because if the star gets more than 1.44 solar masses on it, then another process occurs on a white dwarf. And if it's a binary, if it's going around another star, and then that star goes into a red giant phase, those stars, if they're close enough, that red giant can leak hydrogen onto the surface of the white dwarf and start covering the surface of the white dwarf with hydrogen. And the more hydrogen gas that gets on it, that's more mass. And the more mass that gets on it, the higher the mass goes. And something can happen at a certain point. You get what's called a runaway fusion that might occur on the surface of the white dwarf, where all the hydrogen is converted into helium. Helium, it's a hydrogen fusion process. The entire star, it all happens at one time. And so for a brief period of time, the star gets really, really bright. And then that fades out after a few days to a week or more. That's called a nova. However, sometimes if the star is already close to 1.44 solar masses and the star is bleeding this hydrogen gas onto the surface of the white dwarf, that white dwarf's mass can be driven past 1.44 solar masses. And now that's a huge problem. All right, because now the star not only has the runaway fusion happening, but now it's over the mass limit for a white dwarf star. And so it can explode catastrophically in a supernova. So that white dwarf will explode in a supernova because of this excess gas that went on it. And that's called a type 1A. Roman numeral 1, little letter A. All right, type 2, Roman numeral 2 for the, like this guy. Okay, all right. Type 1A is the white dwarf. So that happens a lot in the universe. We see that. The nice thing about the type 1A supernova is that because, as you asked before, that great question, how do you know the difference? When we see a type 1A, we know it's a type 1A. Why? Because we see the spectrum, and the spectrum shows us exactly what did the blowing up. And so we found that they're always the same. They always are doing the same things. So a type 1A supernova will look the same, no matter how far away it is. So because we know how bright a type 1A supernova typically is, it's what's something called its absolute magnitude. If you brought it to a certain distance, it'll be a certain brightness. Because we know that, we can tell by its actual relative brightness in the sky how far away it is. And that becomes something that we can use to tell distance to distant galaxies and so forth, because we can see these. We actually have, in fact, just recently, what galaxy was that, Darrow? Messier 101.
Yes,
a beautiful face on. You're thinking of that?
Yeah, I was thinking it's probably too late, unless we caught it very early at the beginning of of a program to see how the supernova is doing. Now, we haven't looked at it in a while.
Yeah, it might be really too low. But
Yeah.
we saw this Type 1A supernova, or I'm not sure if it was a Type 2 in that one case or a Type 1A. I'd have to look. But it might have been Type 2. But
M101 was a Type 2, I believe.
Yeah, okay. So Type 2 meaning a core collapse where it does this kind of thing. The whole star just blows up. And it's one star that's massive. Type 1As are binary stars. So that's the major difference. Anyway, but you can see it from millions of light years away. And so we can gauge the distance based on how we know these supernovae act. And that's actually pretty cool. We're going to go to 40 exposures on this and then calm it down and calm me down a little. And then after that, okay, there's 40. Beautiful exposures too. Look at that. All right, so now what we'll do is, this is the eastern veil, so we'll save it. Save it exactly as seen.
Yes, it was the Type 2L core collapse supernova.
Yeah. Okay, so now we've done this beautiful supernova remnant, the core collapse supernova we see here. And now what we could do is get out of this, go back to our 1 second view in night vision mode. And this will allow us now to go to the next object to check out another death in the universe. I don't want to confuse people with Wolf-Rayet stars tonight, but the Crescent. Okay, you know what we'll do? I'll go to the other one that I want to do right away, and that's actually the Dumbbell, which is a different type of star death. All right, and that's measure 27 right here. All right, there we go. So this is a supernova where a star blows up, all right, because it's run out of fuel. But when you're not very massive as a star, like our sun is not very massive, well then you end up doing something different. And our sun is going to die the way this star died. Now that little fuzzy thing right there, you'll see it flesh out into something really pretty amazing in just a little bit here. All right. And as before, from what we talked about, sorry, I went the wrong way. From what we've talked about, the most abundant elements in the universe are carbon, oxygen, hydrogen, and you'll see how the hydrogen and the oxygen figure into this nova, this particular object as well. This is not a nova, it's not a supernova, but it's called a planetary nebula, and that comes from the fact that in a small telescope you might see a fuzzy patch that you could mistake if you're a scientist in the 1700s. You could mistake for a planet. So it's a planetary-like nebula. And the moniker kind of stuck. And people say, all right, well, that's a planetary nebula. What it actually is, it's a star that went into a red giant. But because of the nature of the way red giants form, they tend to puff off their outer layers in their later evolutionary years. And when they do that, they leave a nebula around the central core of the star, and that central core is a very, very hot core that's, again, a white dwarf, like we talked about. All stars could theoretically be white dwarfs if they were less than a certain mass, okay? And so this right here is got a white dwarf in the center, which should become evident when we do another 20-second exposure.
Yep.
All it takes is 20 seconds.
Put your zoom back on too.
What?
Put your zoom back on too.
Well, I'm going to.
Yeah.
Oh, yeah, I will, but I got to remember I'm bringing up the stack, and that takes up this lower part, and then we'll zoom in.
Very good.
All right, so 20 seconds here. We are guiding, and guiding looks good, so we'll come into the stack, and we'll remove the previous one. That was the core collapse supernova there. All right, so removing the core collapse supernova and make way for the Dumbbell Nebula. you'll notice a very distinct difference with these types of nebulae. All right, so that is what this looks like. Now let me just process this a little bit different. It's too long an exposure, but I can affect that because I can dig down in the layers here by doing this. Okay. Now, when we zoom in on this guy, all right, check it out. All right. You see that bright blue object in the middle there? Okay. That bright blue object is the white dwarf. The white dwarf is very, very hot. We're talking 55,000 Kelvin. Look up Kelvin. It's a temperature scale. And we developed the Kelvin scale because we wanted to have a zero value. So we didn't have like negative numbers like minus 10 degrees Fahrenheit or minus 23 Celsius. The lowest value for temperature in the universe is absolute zero. And so absolute zero is on the Kelvin scale. It's a different scale. All right. So absolute zero is minus 273 Celsius. Okay. So now when you look at this blue dot, that blue dot is blue, and you see the other stars in here are not, because it's very, very hot. The hotter things in the universe are bluer, right? It goes from blue to white to yellow to orange to red in order of temperature, lower temperatures. The hottest things are blue. White dwarfs are very, very hot, and because they're stellar cores. Now, this blue thing you're looking at, right, this is thousands of light years away. What's the distance to this? It's like 6,000 light years, 5,000 light years? Do you remember? Daryl?
Sorry. Not offhand, no.
Yeah, it's like 5,000 to 6,000 light years away. And so you're seeing it as it was 5,000 to 6,000 years ago. But this object here, okay, what you're looking at, all right, is you're looking at an object the size of the Earth, and it's 5,000 to 6,000 light years away, yet you can see it. That is how bright this object is.
1,360 light years away.
All right, so 1,300, okay. So either way, this object is still the size of the Earth. You can't see the Earth from half a light year away. Never mind 1,300 light years away. So when you look at this, that blue dot is also giving off a lot of its radiation in the ultraviolet. And in the ultraviolet, it's going to cause oxygen, the green stuff in here, to ionize. So any oxygen atoms that were blown off and puffed off by this star as it was dying are now ionized. And the hydrogen gas, you can see here in the outer ring, this hydrogen gas with little threads here and here, this stuff is also ionized, of course, by this hot white dwarf in the middle. Now, that ionization distance is only a certain amount. Now, if we could tell how far it was expanding, and maybe it could expand to be this big, all right? If it could, and we would know now, we actually know the distance, but it's actually kind of hard to tell distance to these guys, because since we know the ionization occurs only over a certain radius, a certain distance away from that central white dwarf, we could predict how big it should be in the sky if we knew its distance, right? But if we see the gas, let's say that the hydrogen gas continues out here, but the hydrogen gas that's out here isn't ionized, then we know it's at the size, the maximum size it'll be. And because we know that distance, like 1 to 2 light years, we know how big it is in the sky, and we can then calculate its distance. All right, that's what we do with it. Now, if I bring this stuff back, all right, let me bring back some of the detail, you'll see that around it, there's actually more stuff. There's more green stuff out here. And so we know that the oxygen's been ionized way out here. So this is far from done. This particular Nebula is far from finished in terms of showing us the extent, but you see it going out here.
Per what Marc said earlier about why they call them planetary nebulas. Sorry, I'm trying to get my screen back here.
Sure.
In the days of visual astronomy, before cameras, classic astronomers like William Herschel and such, well, they used their eyeballs to look at stuff. And nowadays, amateurs like me still use their eyeballs. And, I remember the first times I ever saw M22 Dumbbell here, it looked like a ghost of a planet. It looked almost like a ghost of the Earth. Mm-hmm. And, you didn't see any color. You just saw gray, but lighter, different parts. And like that wedge there on the left and the one on the right, it looked like continents. Like when you look at the globe of the Earth, you see North and South America. It looked like the ghost of a planet. And that's why they call them planetary nebulas.
Yep. That's really the gist of it. That's really all there is to it. Right? So we've done 18. We're going to go to 19 here. And I'm going to stop it here. I'm going to note it up here. And we'll call it Measure 27. And it's a Dumbbell Nebula. Okay. So we'll save it. Okay. And then save it exactly as seen. All right, now we're going to do something else. We're going to change this exposure to just 10 seconds. All right. 10 seconds and clear this and do it again. We won't do as many. But I want to show you a little more clearly what you can see inside the nebula. A lot of activity, a lot of strange stuff that goes on in here. There it is. You can see that blue star in there. Let's do this. And get the color straight. I just realized that with the moon out, we're going to end up getting kind of a pale glow in here. It's going to be kind of difficult to see, but I might be able to see it if I pull this down. Yeah, see here, all in this area, right in here, you can see there's all these little, let me zoom in, there's like these little details, like little filamentary structures in here. A lot of detail in here. Look at that little thing, Daryl. That's something we've never seen before. This camera shows that very nicely. Look at this little thing. I mean, we got these little details in here that were kind of invisible to us before because they were lost in the resolution, the slightly less resolution. This camera is actually tuned to this particular focal length, that is, the field size. So this gives us a far better view. Yeah, nicely done. I love it. Looks really good. Ray is correct. When the collimation is done in the next few days or so, these images are going to be so much better. So we love them anyway. Because we know what's coming. We see past all this. Alpha Centauri Virgo, how are you? Welcome to SkyTour Livestream. Thank you for joining us. So please subscribe if you can. I mean, we'd love to have you. It's all free. You are free to check out our store if you want to check out what we make and what we do. happy to be of service. Our store is called SkyTourShop on Etsy, by the way, if you want to check out everything up there. You can join our Patreon, but just join, just subscribe, and make sure you check the box and drop down the list and say every notification, so you'll see when we go live. We typically go live multiple times per week, but right now, yeah, it's been a long time, Alpha. So the reason it's been that long has to do with the fact that we have the monsoon going on in Arizona. And remember, I'm in Connecticut, and the telescope's 2,500 miles away. So it takes some, unfortunately, it takes some doing to make sure we can do this on a clear night. I can't just say, oh, cloud's coming in, close it up. I have to do it all. It's a process. I have to disconnect the scope after parking in a certain position. I got to close the roof. I got to do all the double checks to make sure everything's been done, shut down properly. I can do it automatically, but I prefer to do it manually. I don't know. I'm just hands-on that way. I'm an astronomer. This is what we look like, So anyway, the monsoon has caused us to basically have to not do anything. As I mentioned earlier in the broadcast, it's hard when it's a clear night and then you see that the next night's going to possibly have rain. With everything we have that's good, it still takes time to get out to that building. It's out in the middle of the Arizona desert. So we try to schedule visits to the telescope to coincide with when people are around there. And so if something happens, things do happen, things go wrong. It's a green telescope. It depends on solar power. If it's cloudy in a few days, the batteries could die out there, and our scope would power down. With the roof open and the telescope aiming up. Nothing we can do about the power. So that said, we would have someone go out and manually intercede and pull the telescope down, change it, pull the roof closed, and move the roof closed. So that said, it's not 100% perfect, but for the most part, we've been doing this in Arizona now for what, 3 years now, Daryl? 2 years? Daryl's on mute.
I was trying to remember that just the other day.
Yeah, I think we've been going for 3 years or so with this, and we have the East Coast coming back, and we'll get that to happen. Yep. Trisha Ferreira, Nishimura. I was looking at that. That's an early morning comet. That's a pre-dawn comet. And it is visible in September, but you can't see it until after, you get 3 or 4 in the morning is when you can see it. So if I'm brave, I might do that, but I'm thinking maybe I'll wait until later in the season when it rounds the sun and becomes a post-sunset object, and we might be able to see it then.
I mentioned the other day that the comet is going to head south after it rounds the sun, and it's going to disappear in very short order from northern skies, I think.
Yeah, so it has to be something quick that we do, to see it. I want to, and I'm happy to. So we'll do it. I think we'll do it. Okay, and this, of course, is the Dumbbell Nebula. Anthony DeSanto, how you doing? Anthony said something about, looks like a Christmas tree ornament. Was that you? Hey, Science Bob.
I wonder if you meant the Christmas tree nebula, or the Christmas tree cluster.
Oh, he might have.
Which is in Monoceros, of course.
Yes, winter. Yep. I mean, but this could look kind of like a Christmas ornament too, huh? Yeah, this is the Dumbbell Nebula, Anthony. Science Bob says, beautiful. And JSCO 77, nice to see you. Yeah, we're using the new camera. Yes, you got it. It actually affords us better views. It's a slightly more magnified view, and we see more detail, and we've got more pixels per square inch, basically, than before. We have over 5,000 across, and gosh, what's the size here? Let's check it out. It is almost 5,500 by 3672, so 5496 by 3672. That's quite a big array in a small little format. So we're actually getting a lot more coverage.
I assume your files are going to be bigger too.
Well, remember, it's only 1.5 degrees by 1 degree now, not 2 by 1.5.
Well, yeah,
So,
just your pixel count's so much greater.
Yeah.
Could have caused it to be a bigger file, won't it?
Oh yeah, I can't wait to try processing these tomorrow to see what's going on. Yeah, the dumbbell's beautiful, Bob.
I can't wait to see it when you get the collimation dialed in. I'm seeing a lot more here now than we have in the past.
I agree with you 100%.
Fine detail down inside the nebula.
Mm-hmm.
All the whorls and turbulence and stuff there.
Yeah. Cosmic Ray, in selecting a camera for a telescope, you can't just get the best, the biggest array you can get. Unfortunately, because you could oversample your data or undersample your data depending on what you pick. This camera is right dead set tuned to this particular focal length that we're using right now, which is 503 millimeters. Okay, and the previous camera, the 294 MC Pro, was just outside the range. It was in the range, but just the high end. This is dead set in the middle of the range, so we can get really quite nice imagery from this. I've seen the results of this on similar systems, and it's absolutely astonishing what this camera does. You don't know what you're missing unless you actually. You don't know what you're missing unless you actually try and see the difference. Go ahead, Daryl. Sorry.
The number he shows there, is that the right one?
He's not talking about this one. Okay, he's talking about a different camera. He's talking about the 128 MC Pro.
I was under the impression that's what he thought you told him it was. I could be wrong.
Oh no, this is the let me show you the camera. We have the 183 MC Pro. That's what I told him. Now, see, the 128 MC Pro has a 5.97 micron pixel size. What that means, guys, is the size of the pixels in the measurement. A micron's a measurement. The size of the pixels on this one is just 2.4 or 2.7 microns. Very, very tiny. So lots of pixels are used to build an image of, say, just this one section. Okay? Whereas with the larger pixels, you only get a smaller chunk of it, and it doesn't. You don't get the resolution. The smaller pixels, it's like it's like a low resolution image versus a high resolution image. And that's kind of the difference here. No, I said 118, Ray. I've never heard of a 128. This is a 118 MC Pro. So yeah, so this is beautiful. Okay, so we'll save this now. The second one. Save exactly as seen. And we'll come out. And then we'll do one to show you the last in our death series in the universe. And this one is the last one we'll do here. Okay, so let's go check it out. So we showed life in the universe. Now we're showing death in the universe. So let's do this. Let's do this right now. Go back into that. Let's zoom out a little bit. Zoom out a lot of it. And I may have to move it a little bit. I'm not sure. Let's just do a 20-second shot, just like this. It might be right there. I've never shot it with this camera, so and it's on a weird angle, so I'm thrown by that. So you gotta pardon me for that. Okay, so I'm supposed to do a 20-second shot. There we are. Okay. There we go. Let's drop this down to here for now. Oh, I think it's right there. There it is. Yeah, there it is. Okay. So I just have to move it over just a tiny bit. Alright. The moon is also making it kind of difficult to see faint objects. But I just have to move this over here a little bit. So that means I got to go south a little bit. And, oh, that was neat. South a little bit. That might do it. There we go. And this object here is another example of death in the universe. But this is by far, in a lot of ways, the most dangerous one. Because...
might it be more accurate to say dying rather than death?
Yeah, I mean, I was getting to that. It's kind of that's why I'm saying it's the most dangerous one, because it's when people see it, they'll hopefully understand it as I mention it. Yes, that's more accurate technically, but it's not the way I want to characterize it quite yet. But yes. Daryl speaks the truth, because he knows what this is. And now we're going to go and stack it and get rid of the last star death object, the Messier 27, the Dumbbell Nebula. Again, we had the supernovae that blew the star to smithereens. Then we had the slower death, which is this sloughing off of the outer layers of the star. And then we have this one that you're going to see right here. This one is a different death altogether that's on its way. This stuff here, this star that you see right in the middle here, let me color correct, and let me also process a little better, color correct again. Okay, so you'll see this shape. Okay, this star is in the process of dying. All right, and so it is a very special type of star. It's extremely hot, and it's causing the hydrogen gas that it expelled, along with some of the oxygen, to glow from ionization. It's ionizing it. This star is a precursor. It's showing this nebula like we saw the Dumbbell. It looks like a planetary nebula of sorts. But what it's doing is it's sloughed off all these outer layers, and it's blowing them out with extremely powerful stellar winds. Okay, so anything, anywhere in the vicinity of this star in the universe will be sterilized and destroyed. And the star hasn't even died yet, but it's raining death and destruction down on any possible planets nearby and within range because of its high ultraviolet output and the high temperatures of the star. This star has a special name. They're called WR stars, or Wolf Rayet. That's wolf like the animal, and Rayet, Rayet. Okay, like cosmic ray, but Ray ET. Okay, so Wolf Rayet stars, very hot, and now they've sloughed off and sent off these outer layers in violent ejections. And the next thing that's going to happen is, if that's not enough, to add insult to injury, the final chapter in this star's life will culminate with a massive supernova explosion from a core collapse of the main star. And Wolf-Rayet stars come in, 10, 12 or more different varieties. And they are by far one of the most dangerous stars in the universe. You don't want to be near them while they're just being a star, and you don't want to be near them after they go supernova. So they have all the danger of a supernova, and they have all the danger and devastation they can wreak on you of a hot star that's in the process of dying. So they have it all in one package, and when they finally blow up, it's going to be all over with the shouting. Not for us, but for any civilizations nearby, it's going to be curtains. It probably already was. So let's zoom in a little bit. So again, this is called the Crescent Nebula, and for obvious reasons. Okay.
This star is 600,000 times brighter than the sun. So give you an idea of how violent the processes are going on there. It's very big, it's very bright, it's very energetic.
Yeah, so thanks for looking it up, because that's a good thing to know.
When it's supernovas, it's going to be a big one.
Yeah.
Michael, Betelgeuse is not a Wolf-Rayet star.
Yeah, Betelgeuse is just a red supergiant, like Antares is a red supergiant. And the way Betelgeuse, the interesting thing about Betelgeuse is only a few million years old. And the thing is, it used to be a blue O star, the hottest star in the universe. And it quickly evolved to get rid of it used up all its hydrogen. And now it's in a state called, it's the very final state before the supernova phase. It's called the asymptotic giant branch state. And that's where the star has become a red giant, a supergiant, for the second time. And now, in its core, it's fusing elements in shells around the core, as these massive stars do. Betelgeuse is so big that if you put it where the sun is, it would go out all the way to Jupiter, in radius. And you got to make that double for the whole size of the star. That's how big this star is. Incredible. And the color, the reason it went from blue as an O star that's very, very hot to red, which is very, very cool, is because as it expanded, those outer layers, which is what you see, got further and further away from the hot core, so they cooled off. Betelgeuse is so large that in its outer atmosphere, it's actually making like a dust. Okay, molecules can exist out there, whereas inside, the atoms can't even exist. They're plasma. They're free protons and electrons running around and colliding with all kinds of things. Too energetic to even form an atom. But in the outer atmosphere, you can form atoms, and it sometimes forms dust. And Betelgeuse will expel this dust. And when it expels this dust sometimes, you actually end up getting this this cloud of black dust that obscures Betelgeuse a little bit. And the dimming process that occurred with Betelgeuse in the last couple of years, they think, those that studied Betelgeuse, I didn't study Betelgeuse, that it was some of this expelled dust that actually got in the way of the light from the star reaching us. And so Betelgeuse looked like it was dimming. Because, it's a three-dimensional universe. We can't see what's in front of other things sometimes without a lot more research. But one thing about the supernova, when this goes supernova, when any star, when Betelgeuse goes supernova, when Antares goes supernova, and it will, we're going to know ahead of time. And the reason is because these large stars, before they go supernova, they give off a stream of another particle called a neutrino. Neutrinos are released during different processes of normal stellar fusion, but during a supernova, an extraordinary number of neutrinos are released from a star, and they leave the star almost unfettered. Okay, now they many of them get blocked, but the ones that do get out go through the star. They go through you. There's neutrinos going through you from countless supernovae from the universe all around you, going through you in every which direction all the time. So that means that a neutrino stream will come out of the star, and now that actually it's the neutrinos which start the supernova process, but that I'm not going to get into that. But the neutrinos reach us. We see the neutrinos, and if we see where they're coming from, it's hard to capture neutrinos, but we have underground systems because they go right through the whole Earth. Okay, almost unfettered. That's how powerful they are and how efficient they are to travel. But we can trap a few every few billion that come through. We can trap one or two, and if we can actually see which direction they're coming from, then we might have a heads up to, hey, Betelgeuse is about to go supernova. We're getting a neutrino stream from it right now. And if you looked at it with your telescope, it would look just like it looks now. Perfectly normal. The reason is because the supernova is a physical process where physical materials moving out from the core, from the exploding, from the rebound of the core, where the core is collapsed and bouncing back outward. And that blast wave moving out is stuff. It's not light. It's stuff, physical protons and electrons that are moving out from the core. So it's going to take hours for that shock wave to reach the surface of Betelgeuse and burst outward and rip the star apart. So if you were a star and you suddenly released a bunch of neutrinos, you only had hours left to live, because it would mean that's when the supernova blast wave reaches the surface. That's pretty crazy, but that's what it is.
For Michael's question, Michael, Betelgeuse is a red supergiant, and remember when we've talked about, like, "Oh, be a fine girl, kiss me," blue stars are hot, red stars are cool. Betelgeuse is big, but it's a cool star, and that's why it's making atoms and molecules, as Marc described. Basically, it's puffing off lots of soot. When we look at a Wolf-Rayet star like this, the Wolf-Rayet star there, that thing is 70,000 kelvins temperature. It is an extremely hot star, as compared to Betelgeuse being a cool star, relatively speaking. Just a few thousand kelvins, probably, if it's cool enough to put off soot.
It's probably 2,500 to 3,500 Kelvin on the surface out there. Yeah.
So when this one goes, it's really going to go.
Yeah, it's going to be exciting. Yeah, this one is due, you know. So, you know, hey, it'd be so cool to see a supernova remnant in Cygnus along with the veil. That'd be kind of cool. Okay, Ray, this is the 183. It's the 183 MC Pro camera. That's this camera we're using.
183.
Yes. So I hope you folks have enjoyed this tonight. I'm going to just label this the Crescent Nebula, and then we will save it. It is 143 here. Too. Yeah, this
compared
is
to
this
the old
is
camera.
Yeah, this is 37%. So the entire image looks like this. That's almost double in size.
Oh.
You know, so that's really nice. And the bright rim around here again, moonlight. But our filters, as you can see, allow us to really show some cool stuff. All right, so we'll save this here. As you can see, our wind has died down, so our guiding is now flawless again. See what I was saying though about? See what I was saying though about the fact when the telescope's pointing up, the collimation issue is reduced.
Yes, I was just going to
That's
say
because,
that.
okay, because the thing on the front of the telescope, it's got a little bit of play in it because it just had the screws have to be tightened down. That's all that's wrong with it. It's a 5-minute fix, and it's like it's 2,500 miles away. So, Marianne's gonna probably head out there. Okay, so we saved this out there. I think I said save just as it was. Yeah. Okay. Well, there we go. So that's birth and death in the universe. I hope you enjoyed this, guys. And, you know, again, we'll do this again very soon. And I don't mean 4 weeks from now. I mean, as the moon... the other reason why we don't do it is because the... Pull this out of here. Go away. The only reason we don't do it is because when it's a full moon, we get too much stray light. And so it's not the best thing to do, you know. So that's not a good thing. So, excuse me. But we'll do this soon. Okay.
Are you okay?
Yeah. I'm fine. I'm just I had a cough, so I had to quell it. Okay, so I'm hoping that you guys will come back and join us again. We will be back soon. The telescope actually performed reasonably well tonight, even though there's a little bit of a collimation error. And then we'll look at other things north of Cygnus. We'll look at the North American Nebula. We'll look at we'll look at nebulae farther up in near the North Pole, actually, which are really cool. So I hope you guys liked it. Make sure to, you know, for those that haven't, subscribe. Head out to the store at SkyTourShop on Etsy and enjoy out there and check out all the things we offer. And if you have any requests, by the way, remember, you can send them to me. This is my address right there. That's my email. So you can send that to me. That's the private email. Actually, my public email is contactskytour@gmail.com, but I'm not the only one that gets that. This is the only one. I get this one. Nobody gets this one but me. And I didn't want to clog our nonprofit email with other things. I may change that. Okay. So anyway, I hope you guys have a good night. We're going to head out of here now, and being that it's almost 2 a.m. So let me know in comments on the video or anything, what else you'd like to see and what you thought of it. And I look forward to seeing you all again. So you guys have a good night, and I'll see you the next time. Keep looking up.
Good night, everybody.
There you go. Good night, everybody.